So I'm really happy to have Jennifer Barnes here to talk to us about multi-messenger astronomy from gravitational waves and electromagnetic radiation. So it's a really exciting time for this. So Jennifer went to Macalester College for her undergraduate degree, and then went to UC Berkeley and worked with Dan Kaysen on kilonovae and predicting the signatures of kilonova, and did a lot of important work there. And then she finished there recently, and she's now a NASA Einstein Fellow at Columbia University, working with Brian Metzger, I think, mainly. Is that right?
That's right.
And so we're really glad to have you here and interested to hear what you have to say.
Okay, well, thank you so much. So as Luke explained, I'm going to be talking a little bit about the first multi-messenger observation of a neutron star merger, which I'm sure a lot of you know happened on August 17th of this year. So I'm really excited to tell you a little bit about what we've learned from that observation. So what you have to look forward to today. Before I go into too much detail about the detections themselves, I'm going to do my best to place mergers and all of the phenomena that accompany them into their astrophysical context, and explain a little bit about the various branches of astrophysics that these observations of these events can allow us to study. I'm then going to talk about the observations, both in gravitational waves and in multiple wavelengths from the electromagnetic spectrum. And I'll talk about what we learned from them, and then address some outstanding questions that remain that we can look forward to addressing more in the future. Okay, so we know that the radiation, the gravitational radiation from this neutron star merger had to travel roughly 130 million years to get to us. But the story of this merger actually starts a long time before that. And that's because compact object mergers are a long, long time in the making. So compact objects, of course, are the remnants of massive stars that have gone supernova. So every compact object binary starts out as a massive star binary. And it then goes through these processes of stellar binary evolution, some of which are better understood than others. But the important thing for these systems is that some of these processes draw the component stars close enough together that they aren't disrupted when each component star goes supernova. So after both supernovae have occurred, what we're left with is a gravitationally bound binary where each component star is a compact object, so either a neutron star or a black hole. And from there, all we have to do is wait. The primary ingredient is time, but you do need a lot of it. So the gravitational, this binary is going to emit gravitational radiation, and that's going to draw angular momentum and energy from the system, and it's going to slowly, slowly cause the orbit to shrink. So to give you a sense of the scales involved, if we start off with two solar mass neutron stars that are at an initial orbital separation of about a solar radius, it's going to take 100 million years for the binary to merge together. But eventually it will merge, and then some really exciting things happen. So the first is that the final several orbits are a really luminous source of gravitational radiation. So we get a burst of gravitational waves. And then when the merger happens, assuming that the system contains at least one neutron star, we should also get some observable electromagnetic radiation, which can give us even more insight into the system than the gravitational waves alone. So here I've organized some of the EM counterparts we might see in a timeline. So okay, right away, directly following the merger, we might see a short gamma ray burst. So we think that compact object mergers are the progenitors of these short bursts. The long bursts we know are associated with core collapse supernova, but until very recently, we didn't have a handle on what might be driving the short gamma ray bursts. So if that is the case, then we would expect to see the gamma ray burst, roughly coincident with the merger, assuming that our line of sight intersected with the beaming angle. So we know that gamma ray bursts are beamed emissions, so they have to be pointing toward us in order for us to observe them. We could also observe the afterglow, which would evolve on slightly longer timescales than the GRB itself. Okay, then we can think about optical transients, and in particular radioactive transients, which is what I'm especially interested in. So these transients are not associated with relativistic jets like the GRB. Instead, they're associated with material that's torn from the neutron stars during the merger. It becomes gravitationally unbound and is ejected out into space. So these are generally powered by radioactivity. So this could be the decay of free neutrons at the ejecta front. So that is thought to perhaps give rise to something called the neutron precursor, which is a very short, bright optical UV signal. So as I said, that's somewhat speculative, but more robustly, we expect an optical signature associated with the radioactivity of R-process nuclei that are produced during the merger. So the neutron-rich material is torn off the neutron star, it's flung out. As it decompresses, it's thought to undergo R-process nucleosynthesis, and then the heavy unstable isotopes built up during this nucleosynthesis channel are going to decay. That's going to heat the debris cloud, and it's going to glow. So that's what we would observe in these transients that we've named kilonovae. And kilonovae, generally come in slightly different flavors depending on exactly how the mass is ejected from the system. So we have some dynamical processes such as tidal stripping or dynamically squeezing from when the two neutron stars crash together. And then you can also have a secondary outflow from an accretion disk. So if some material is in a disk surrounding the central remnant after the merger, there are additional ways to transfer energy to that disk that would unbind some of the material and give you another. Right. It's theo-observational. So what I'm presenting right now, and I should have made that clearer, is kind of a theoretical overview of what we expect, and then I'll talk a little bit about how observations have kind of informed theory and given us some idea of where we're on the right track and where we're not. So yes, theorists have identified different methods by which mass could be ejected from the system, and this might give rise to, each might give rise to distinct kilonova signatures. So these radioactive transients are, as Luke mentioned, what I've focused on, for my PhD and in my postdoc so far. So that's going to be a point of focus today, but they're by no means the only electromagnetic signature that we could expect to get from these systems. So finally, the last transient that we might get, months or even years after the merger, would be a radio afterglow. So as I said, some ejecta is released from the system. Eventually, this material is going to collide with the ISM, and that should drive a radio signature. Okay, so studying these systems, via one or a couple of these messengers would be a really exciting opportunity to study a lot of very interesting astrophysical phenomena. For starters, since we know these stars have to proceed through all of these stages of binary evolution, understanding what stars merge and what the demographics of these merging populations are could provide really important constraints on single and binary stellar evolution. Okay, obviously it's going to give us a chance to directly measure dynamics in the strong gravity regime, which is going to be an important probe of general relativity. They also give us another context in which to study astrophysical jets, assuming we're right and they do drive short gamma ray bursts. Finally, both the gravitational and the, or not finally, almost finally, the gravitational and the electromagnetic radiation is mediated by the neutron star equation of state. So measuring these systems will help us better understand the architecture of neutron stars. Okay, and finally, and perhaps the thing that is most interesting to a lot of people in this room, as I mentioned, we think that some of the signatures, some of the electromagnetic signatures of these systems are driven by the decay of R-process elements, and we suspect mergers may be the dominant site, or even the only site of R-process nucleosynthesis in the universe. So observing the radioactive component of the EM signals will help us understand where the heavy elements in the universe are made. Okay, so that was kind of a theoretical overview, but what had we actually seen? Here's where we were as of August 16th, 2017, which somewhat coincidentally is the day that I left Berkeley to start, to move towards starting my postdoc work at Columbia. Okay, so as of then, considering all of these pieces of the theoretical picture that we had constructed of these binary mergers and how they form and what signals they generate. Okay, so we knew that compact object binaries were out there because we observed them as binary pulsars, and we even knew that these compact object binaries were shrinking consistent with the predictions of general relativity. So this little icon shows the orbital decay measured for the Hulse-Taylor pulsar, which represents the first indirect detection of gravitational waves. Its orbit was found to be shrinking, consistent with what you would expect if it was gravitational radiation that was taking the energy and angular momentum out of the system. So since then, we've found several more compact object binaries, and we've even found a handful of systems that would have merger times less than the age of the universe, which tells us that not only are we making compact object binaries, we know that the universe is capable of making compact object binaries that would merge in a time frame that would allow us to observe them. We had seen gravitational waves, but only from binary black hole mergers. So LIGO had detected 4, I believe, but we were still waiting for a system where one of the components was a neutron star. Okay, we saw a lot of short gamma ray bursts, and we weren't able to conclusively tie them to any progenitor. So unlike long gamma ray bursts, which have been pretty conclusively associated with core collapse supernovae, we just saw these bursts and we didn't quite know where they came from. There had been no unambiguous detections of radioactive transients, although people had searched for them in the afterglows of short gamma ray bursts. So on the theory that if we were right about the short gamma ray bursts, you should see short gamma ray bursts coincident with some of these radioactive signatures. There was, there have been some promising signals, notably the short gamma ray burst 130603b, in which very prominent infrared emission was detected, suggesting radioactive transient and a kilonova in particular. But again, there was nothing that was a really clear smoking gun signature of these systems. We also hadn't detected these radio afterglows, but given kind of given the huge time elapsed between the merger and when the radio signal turns on, and also just given how much these signals can vary depending on the parameters of the system, it's not really surprising that we hadn't been able to just pick them up on their own. Okay, and then seemingly overnight, pretty much everything changed. So on the morning of August 17th, the LIGO Virgo network of detectors picked up a chirp that was characteristic of a binary merger. So that's what's shown in the top panel here. This is a frequency power spectrum. And you can see there's kind of a light band moving upward. And what that is showing you is that you have a lot of power coming out at these low frequencies. And then that low frequency source is becoming a high frequency source. And that's exactly what we expect in the case of a compact binary merger. Less than 2 seconds later, we got some additional information in the form of a short gamma ray burst. So the signal that was picked up by Fermi and integral is shown here in the bottom panels. So you can see just to the right of this gray line, we have a spike in gamma ray bursts. So gamma ray burst localization with these instruments is really tricky, but in combination, information from Fermi and integral was, we combined that information and we were able to determine that, and when I say we, I mean not me, other people who actually do the observations. These other people were able to determine that the location of the gamma ray burst on the sky was consistent with the error localization from the LIGO trigger. Okay, so even just within the first 2 seconds of detecting the merger now, we have a lot of really exciting information. So to suggest that what we were dealing with was not another boring binary black hole merger, but something that actually involved a neutron star. So for one thing, the masses that were inferred from the gravitational wave information were right around what we would expect for a neutron star merger. So yeah, they're kind of between 1 and 1.4 solar masses. So this is not a binary black hole merger. It's more likely to be a neutron star merger. And then the fact that we have this coincident gamma ray burst pretty much rules out the possibility that we're dealing with 2 black holes, because you need matter to make a gamma ray burst. Okay, so we had a binary neutron star merger, and we actually had a really great chance at following it up and successfully detecting further emission from it. So that's because, one, the localization was very good. Somewhat ironically, this was partly due to the fact that the merger happened in Virgo's blind spot. So the fact that you saw a signal in LIGO Livingston and LIGO Hanford and then couldn't see anything very clearly in Virgo allowed the LIGO team to pinpoint the location with a lot of accuracy to 30 square degrees, which is compared to like roughly 100 or even a few hundred that you see sometimes. It was also determined that this was a really close binary, so 40 megaparsecs, which is well inside the threshold. So you might expect, just because of geometric considerations, that most detections would occur at threshold. This one actually occurred well inside that. So with this information, electromagnetic observers identified 50 potential host galaxies to follow up and got to work looking for an optical counterpart in each of them. And this actually probably launched what might be the largest EM observational campaign ever. So there were dozens of groups that were looking for signals all across the electromagnetic spectrum. And it didn't take long for them to identify an optical counterpart, which you can see in these bottom panels. So the top panel is actually from the LIGO-Virgo collaboration paper, and it's a really nice illustration of all of the observations that were taken in all of the bands and how those depended on time. So just for clarity's sake, I edited out the part where they listed every group contributing in every region of the electromagnetic spectrum, but you should look up the paper if you haven't, just to get an appreciation for, you know, what a huge cooperative effort it was to get all of this data. But anyway, the optical observations are shown in these lower 6 panels here, indicated by the crosshairs. So SWOPE was the first telescope to localize something that was about 11 hours after the merger, and then, you know, within an hour after that, many other groups had identified the transient and were able to follow up and get a really complete optical picture. Alongside that, there were people looking in the X-ray and the radio, and they were able to identify activity at those frequencies from this merger as well. And so, you know, now we have electromagnetic observations from a really broad region of the electromagnetic spectrum in combination with a gravitational wave signal, and all of that gave us a really, really rich picture of the merger and the emission that it produced. So what I want to do now is highlight some of the key, I guess, the key inferences and some of the key puzzles from those observations. So the first thing I want to focus on is actually not the kilonova, even though that's my main focus overall. I want to talk for a second about the gamma ray burst, because it was a little bit mysterious. So I'm going to be discussing both the prompt emission, so the gamma rays that were observed at that 1.7 second delay, and then a little bit about the afterglow, which was observed in X-ray and radio. So in some ways, GRB 170817 is a typical burst, but there are also a few things that are a little bit strange about it. So first of all, it's much weaker than cosmological short gamma ray bursts. So the overall gamma flux was consistent with other bursts that we see, but this system is so much closer than anything we've seen before that the luminosity inferred is a factor of 10 to the 2 to 10 to the 4 times weaker or less luminous than other bursts. So there's a question of, you know, why is this burst so weak? The second thing is timing, right? There's this almost 2-second delay between when we see the merger in gravitational waves and when we see the first gamma ray burst. And so there's still some open debate as to what the cause of this delay is. So some of it is just relativistic kinematics. You have a jet that's moving not quite at the speed of light, and it takes a while for gamma rays to leak out of that system and make their way to us. You know, but there are some other factors that could be at play as well. It may be that you need a black hole in order to launch a burst. And in that case, we have to think about the time that the system would take to go from perhaps a hypermassive or supermassive neutron star that's rotating very quickly, how long it would take to go from that into a collapsed black hole that would be capable of launching the burst. It's also possible that, you know, you have some jet propagation effects, so it takes a while for the jet to actually burrow its way through the ejected material. So this is like the cocoon hypothesis, right? The theory that the emission is coming not from a clean jet, but from a shocked cocoon surrounding the jet. It could also just be, you know, viewing angle effects. So we might be off. Well, we know that we're off axis from the rotation axis of the merger, and this could be affecting the time that it takes the gamma ray bursts to make their way to us. The third thing I want to highlight that's a little bit interesting is that we actually have 2 components to this burst, which is not so typical. So you can see in these higher energy X-rays, the hard gamma ray burst spectrum looks pretty normal, fairly consistent with other observed gamma ray bursts. But then we have this softer component that seems roughly thermal with a temperature of 10 keV. So that's also a little bit puzzling and something that people are still working to figure out. Okay, so the picture is a little bit clearer when we move on to studies of the afterglow, which were observed in the X-ray and the radio. And the signals that we're getting out of the afterglow seem to be pretty consistent with an off-axis jet. So as I said, we know from gravitational waves that we're not quite on that we're a little bit off the axis of rotation of the binary. And that's the axis along which we expect the jet to be launched. So that can affect the way we see the gamma rays, and also it can affect the appearance of the afterglow. So there's a diagram here just kind of showing in a very schematic sense what that looks like. You have jetted emission. Most of the gamma rays are beamed into a very narrow opening angle that's given by approximately the inverse of the Lorentz factor that describes the jet. If we're not within that initial beaming angle, we're not going to see much of the early emission. We have to wait until the jet slows down, till gamma decreases, the emission becomes more isotropic, and some of it makes its way to us. So what I'm showing in these plots are X-ray observations from Raffaele Marguti's group, as well as these radio observations from Helenen et al. And they just compared the observations that they had gotten against models expected for an off-axis afterglow. And they found that they could explain their observations with a pretty simple model, assuming that our offset from the rotation axis was about 20-ish degrees, which is consistent with the constraints that were derived from the gravitational wave signal. Something kind of exciting about this is, we have a little bit of tension here because some people looking at the GRB are proposing like cocoon emission or some other effects to explain the gamma ray burst signal. And the X-ray and radio seem to be consistent with just a simple off-axis afterglow. But the predictions for the X-ray and radio emission from these two scenarios are actually consistent for the timeframes that we've been able to observe so far. And right now, the system is behind the sun, but it's going to come out from behind the sun in a couple of weeks, and then we'll be able to get some observations at later epochs where the predictions for these two scenarios diverge. So, within a month or so, we should have some observations that will better constrain what's really going on with the beamed emission from this merger. Okay, so now I'm going to talk a little bit about the optical and near-infrared signals, which are associated with the kilonova. Okay, so in very broad strokes, these are, yes, this is the information we have. So I'm showing bolometric luminosities. That's just, all of the luminosity as a function of time here on the right, and then some broadband light curves on the left. Okay, so I'm sorry, on the right. So looking on the left, you can see that bolometric luminosity is roughly in line with the energy that we expect to be released if you have a few hundredths of solar mass of material undergoing our process decay. So that's actually, it sounds low, like if you study supernova or stars and you're used to thinking in terms of solar masses, but that's actually on the upper end of what we expect to get out of these binary neutron star mergers. So this is kind of, it was a pleasant surprise to see something that was actually this luminous. And then we also see from the broadband light curves, this is showing, so I don't know if everyone's an astronomer or if I have some nuclear physicists, but if the UGR are kind of like the optical bands, and then if you go over to the very far right of the plot, as you go up the plot, you're getting to lower and lower energy bands. So what you see is that you have an early bright optical component, but that fades away very rapidly and gives rise to a longer lived redder transient. And we can see this in a little bit more detail when we look at the spectra. So this is the time evolution of the UV and optical spectra. And then from a separate paper, we can see the infrared spectra. So we see the same blue to red transition that we identified from the broadbands, but there's some additional information here. So the first is that we see the spectra go from being very featureless to having these very broad absorption features, which gives us some handle on the velocity, although it's still quite fast. If anyone studies supernova, you might think that these kind of have feature widths that are similar to broadline 1Cs, which we know are moving at around 0.1 C, and the velocities inferred from these spectra are actually a little bit higher. We think they're characteristic of like 0.2 to 0.3 C velocities in the ejecta. The other thing we see is that in some stages, the spectra appear to have two components, and that they can be it turns out they can be fairly well approximated by two black bodies at different temperatures, which is an interesting point that I'll come back to a little bit later. Okay, so what conclusions can we draw from these observations of this single system? The first one is kind of, it feels almost obvious to say now, but it's actually really kind of profound. The fact that we can see this thing in the first place tells us that there must be some sustained energy input, right? If we just dumped a lot of energy at the beginning, into an exploding system, all of that energy would be lost very rapidly to adiabatic expansion, and we wouldn't be able to follow it up for weeks as we were able to do. So we can be pretty confident that this is powered radioactively, and we believe that the specific radioactivity channel involved was the R process, nucleosynthesis. So this is partly due to just theoretical considerations, right? You need really particular conditions in order for the R process to proceed. In particular, you need to have a very high neutron flux, and ripping apart a neutron star is a great way to get that high neutron flux that you need. But the observations also seemed consistent with a couple of really important predictions specific to R process nucleosynthesis. So the first is that the decline of the luminosity was, the decline that we saw in the bolometric luminosity was consistent with the decline in the heating rate that we expect to see from the R process. So the fact that the R process produces a very wide range of nuclei that are all decaying on their own timescales and with their own energies gives you a power law heating rate, as opposed to like a supernova where you have your radioactivity dominated by just a few decay chains and everything is pretty exponential. So yeah, the bolometric luminosity was consistent with this idea that the energy generation should fall off like a power law. The other thing is that we saw significant near infrared flux, which we believe is a fingerprint of a composition heavy in some of the lanthanide elements that we know are produced by the R process. So just shown here mostly as an illustration is an example of the spectra that you get out of a kilonova-like transient, depending on the composition. So if the composition is lighter and confined to the iron group elements, you get kind of a bluer spectrum, like what we see in the black curve. If instead you mix in some lanthanides, which are produced by the R process, you push your emission out into the infrared, and you get a much redder transient. Okay, so the reason for this is the atomic structure of the lanthanides and the actinides. These elements have their valence electrons in an open F shell, right? So there are like 14 spots for electrons in a valence F shell. Well, a lot of the lighter elements, you know, iron, but also some of the lighter elements produced by the R process have an open D shell, which is smaller. So the larger F shell, just from a symbol combinatorics argument, means there are many more possible electronic configurations. So there are more ways to move the electrons around and give you slightly different energy configurations. Photons are, you know, trying to escape the ejecta. They're moving along. They get absorbed by an atom. They excite that atom's electrons into a different energy level configuration. And then, you know, later the atom de-excites and the photon can move on its way. But that's a main process by which photons trying to escape the ejecta are going to be hindered on their way out. So the more electronic configurations we have, the more ways there are, the more opportunities a photon has to bump an atom from one configuration to another, and the harder it's going to be for that photon to be escaped, or to escape, pardon me. So that's that idea, this photon hindrance, is quantified by what we call the bound-bound expansion opacity, which is what's shown here in this plot. So unfortunately, this is not experimental data because we don't have a lot of the experimental data that we need to calculate the bound-bound opacity for some of these R process elements. So instead we use synthetic atomic data. But we calculated the bound-bound expansion opacity for a handful of the elements that are produced by the R process. And you can see that this F shell versus D shell is a really useful predictor of the overall opacity that you get out. So if we have a significant, you know, portion of the mass tied up in these open F shell elements, it's going to make it harder for photons to get out, and it's going to push the emission out to redder wavelengths where the opacity finally starts to drop off. And that means that if we have a lanthanide-rich ejecta, and when I say lanthanide-rich, I mean we have a quantity of lanthanides consistent with what we expect from a robust R process that produces through the third peak, so that's maybe 10-ish% by mass, we would expect to see a lot of red emission with a subdominant contribution from the optical and UV bands. But remember that that's not totally consistent with what we saw. What we see instead is a rapidly fading optical component and then an infrared component that becomes important only later on. Right, yes, yeah. So I mean, yeah, everything in that first row. So yes, not just lanthanum. Right, so we seem to have this two-component or a light curve that suggests multiple components. And we also have spectra that are consistent with that, right? And that suggests that we might have emission from two distinct pieces of material. So one that's lanthanide poor, giving you the early emission, and one that's lanthanide rich, contributing to the rise of the red glow at later times. Yeah, and that's actually not, excuse me. So radiation transport modeling shows us that this two-component model can do a pretty good job reproducing the features that we observed. So these are the results of radiation transport simulations for a model that has a lanthanide poor part and a lanthanide rich part. I guess one caveat that I want to make sure I address as I present these is that when we show the composite spectrum, this is just adding flux from two independent models, and we're not considering the interaction of the two ejecta regions. But there are reasons that I'll explain a little later to suspect that that's probably not such a bad approximation. If the two regions are spatially distinct, that should be just fine, especially for a first approximation. Right, so you can see with this model, everything early on looks pretty blue. The spectrum and the broadbands are dominated by this blue component, which is lanthanide poor. But then, that's lower opacity. It fades away pretty quickly and kind of burns out. And then we see this longer-lived, low opacity lanthanide rich component taking over. And the turnover seems to happen around a few days. Okay. So it might seem like we're complicating things by invoking multiple components for this system and saying that we have to have different nucleosynthetic outcomes happening for the same merger. But the fact that we see this signature actually isn't that surprising. So it's well known that the R process can produce different abundance patterns depending on the initial conditions. So in particular, the more neutron rich we are when the R process starts, the easier time we have making heavy elements, such as the lanthanide and actinides that we need to contribute this high opacity. So that's what's shown here in a paper by Jonas Lipner and Luke Roberts, who's sitting in the audience. YE, which just kind of measures the inverse of neutron richness. So low YE, many neutrons, very neutron rich, high YE, neutron poor, relatively. So yeah, low YE compositions give you a really robust R process, and we can very easily make these isotopes with mass numbers out to 250. As we start dialing down the neutron richness and increasing the YE, we make less and less of these heavy elements. It looks like YE of about 0.25 emerges as a threshold value. Above that, we can, make these, make enough heavy elements, including the lanthanides and actinides. And if we go much past that, we have a very hard time, and we're restricted to these lighter R process elements. So what we're really, what we are really talking about when we talk about neutron richness is actually neutrino irradiation. Right, because if you start by ripping apart a neutron star, you're pretty robustly neutron rich, and it's hard to get around that unless you irradiate this material with neutrinos, which can turn some of your neutrons into protons and drive the YE fraction up. So yeah, in that way, the composition is a proxy for YE. YE in turn is a proxy for neutrino irradiation, with robust heavy element production standing in for less neutrino irradiation, and a lower YE and a lighter R process indicating more neutrino irradiation. So, and it was actually realized by people doing some of the GR hydro modeling of these systems that it's possible that the same neutron star merger could give rise independently to each of these conditions, and therefore host distinct R processes that would have different final abundance patterns. Specifically, we might expect light R process to be produced by, or to be produced in shock-heated dynamical ejecta. So this is ejecta that's thrown out of the system when the two neutron stars crash together. You have a very violent collision. Some material is ejected from the contact interface when the two neutron stars coalesce. And that material is really, really hot, so it can self-irradiate itself. It can, self-irradiate, produce neutrinos and drive its own YE up. And then we would expect the heavy R process to be produced in either dynamical ejecta from tidal shredding. So as the neutron star completes its final few orbits, some material can be tidally torn off of the component neutron stars and released. This material would be very cold and have a really low YE. So that should go, that should very easily have a robust R process. And then it's also possible to get a secondary neutron-rich outflow from an accretion disk after the merger that surrounds the central remnant. Okay, so with these ideas, we can combine these ideas with our observations to move toward a more comprehensive picture of this event. So the picture that we have so far is that some shock-heated dynamical ejecta moving pretty quickly is providing you with this early blue emission. After that fades, we see sort of this much longer-lived red transient evolving on slower timescales, consistent with its high opacity. Yeah. Okay, and so to finish up, I'm just going to show some animations that I think nicely tie together this picture and show how this picture gives rise to the electromagnetic signatures that we actually observed. Okay, so first I'm going to show some very coarse broadbands. So these are kind of blue and red light curves based on this two-component lanthanide-rich, lanthanide-poor model that we published in a kind of a theory overview paper in Nature earlier this month. And then that will be compared again to some observations. So let's just take a look at that, and then I'll talk a little more. Okay, so right, early times were really, really dominated by blue emission, but then that falls off very quickly. And then we have a slower moving red transient. So someone at a talk I saw recently said animations take a long time to make, so you should take a long time to appreciate it. So I'm just gonna play that again. I thought I was. Yeah, so what we're showing is data and model on the right, and then kind of a cartoon picture of what's actually going on in the ejecta on the left. Okay, and the final thing I want to show is this effect on the spectra of this two-component model, which is consistent with the same basic picture, but gives you a little bit more detail because now you're breaking down the radiation. But yeah, again, you see hot and blue early on, cool and red at later times.
Does this model take into account any viewing angle, or are we actually looking at it?
No, so this feeds really well into one of the lingering questions I want to discuss. But yeah, these are all based on one-dimensional models that are superposed. So there are complexities that we're not accounting for here. And this is a first-order attempt to understand what the system looks like. Okay, so with that segue, I just want to point out some questions that remain, lest you think all our work is done and there's nothing more to be learned by studying these systems now that we've observed the first one. So first, in the realm of GRB physics, what explains the GRB we see? In particular, why is it so weak, and why does it have this unusual thermal component in weaker X-rays? So just to remind you, some possible explanations that have been proffered have been a cocoon, or perhaps a structured jet, so where the jet, instead of being uniform within its solid angle, actually has some variation, some angular variation. Okay, the other question is, what is the source of the bright early optical emission? I've made the argument that it's lanthanide poor material, but there's still this question of how do we get the amount of lanthanide poor material that we need, and is that consistent with other constraints that we get on like the neutron star equation of state, for instance? Is it hard to produce this much mass? I guess a follow-up question to that is, do we actually need to produce this much mass? Because as I said, a lot of these models are based on these one-dimensional radiation transport simulations, and there has not yet been work done to figure out, you know, whether we can get the same effect, or whether we need to incorporate viewing angle effects, or you know, whether the 1D models are actually a good stand-in for a more complicated configuration. And then the fourth question, which is something that I'm interested in, is, you know, did we really make the gold? So we have a very broad brush now that we can use to talk about what the composition of the ejected material is in these mergers. We can look for a blue signal or a red signal, and we can say, you know, we either did or did not make a substantial quantity of some of the material that causes this high opacity. But a lot of the elements that we still need to make with the R process lie beyond the lanthanide row of the periodic table. So that would be like the gold and the platinum. And then of course we also somewhere in the universe have to make the actinide elements, like, you know, your uranium and your plutonium. So it's very difficult right now with, you know, this very coarse resolution that we have to study these light curves and spectra, to identify whether we really made the full range of our process material, or, you know, whether we just made some lanthanides but didn't get all the way up to the heaviest elements that our process is capable of producing. So trying to think about potential diagnostics for giving us a narrower brush, I guess, that we can use to understand the light curves and spectra in more detail is something I'm really interested in working on going forward. Okay, so that's all I have for you. I think for the first time in my life, I finished a talk a little early, but I'm happy to take any questions that you have.
So, right, a lot of our inferences for the neutron star majority in the local universe is based on Milky Way double neutron star systems that we know about, and in particular a couple of systems that have very short merger times. Right, this source obviously went off in an old galaxy, probably doesn't, you know, have substantial recent star formation. So is it going off in an early time galaxy like that? Is it like interesting at all? Is it like one sigma interesting? Does it raise your eyebrows, or is it just, you know, that's what happens when you want?
Yeah, I think probably the latter more than anything. I mean, it's not, you know, just because these systems take so long to be formed and then to shrink and then to merge, it's not necessarily surprising that we would see them in old galaxies. And actually, you know, you see, so maybe someone is a short gamma ray burst expert, but I think you generally tend to see short gamma ray bursts in these older galaxies as well. And you don't really see them at all in like spiral galaxies. So I guess in some ways, maybe that's the interesting thing. But yeah.
Could you repeat the question going forward? Just so that
Oh yes, of course.
Other questions?
There must be a lot of simulations of these kilnover events. I wonder how do they differ?
Okay, so the question was, how do simulations of kilinovae differ? And they're actually surprisingly consistent. I think the thing you have to keep in mind when you talk about these simulations is that you have a propagation of errors, right? So you have to start with 2 neutron stars and merge them together. And then, you know, grid-based simulations compared to these smooth particle hydrodynamic simulations can give you slightly different outflows. You also expect to have some natural variability just because you're going to have, you know, different component masses, different mass ratios. And then there's also some uncertainty in the neutron star equation of state, which can all have an effect on the masses and velocities of the ejecta that you ultimately get out. So yeah, and then kind of the range of outcomes you get from those simulations are propagated forward into the post-processing that's done to determine what the nucleosynthesis should be. So then you can get some differences in the nucleosynthesis. And then finally, those are the ingredients that we need to feed into our radiation transport simulations, which is, I guess, my area of expertise. So yeah, what you get out of radiation transport simulations depends partly on what you get in. And if you start assuming you have different masses and velocities, what you get out is going to look very different. And then I think the other major uncertainty that comes into play only at the radiation transport stage is what is the relevant atomic data. So, what do we think the bound opacities are? What are they for different elements, and how should we add that all together? And there actually aren't so many groups that are working on that. I think there are 3 or 4. And interestingly, if you just look at the synthetic atomic data that is calculated to determine these opacities in the composition, you get a lot of overall agreement. So part of that is just due to the fact that bound opacity in an expanding medium is a statistical measure, right? It's not so important that we nail down every transition at exactly the right energy and assign them all the right oscillator strengths, et cetera, et cetera. The important thing is that we roughly know how many strong transitions there are and what the density of them is in wavelength space. And so, that gives you a little bit of leeway. If I say the lines are, here, 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 and you say the lines are here, 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 we both agree that there are 3 lines, between lambda 1 and lambda 2. That's going to give us some, roughly the same expansion opacity. There has been some disagreement recently on the appropriate way to calculate this quantity for an expanding medium, and that gave rise to some differences in kilonova simulations, but I think we have kind of overcome that recently, and we're converging. So now we think we have pretty consistent data, and we're also converging on a methodology. So yeah, I think a lot of the differences that you see come from the differences in the ingredients that you put into the radiation transport simulations, which probably reflect the natural variability that we expect to see if we observe a lot of these.
Yeah, how accurately do you think ultimately one will be able to say how much matter was actually
Okay, so yeah, the question is how accurately we can infer ejected mass from observation. I think we're in the right ballpark now. I think it's going to get better once people start doing more multidimensional simulations, and then that should give us an idea of whether we really need to account for viewing angle effects. The ideal situation is that we find that viewing angle effects are maybe not so important, and that our 1D models are very, very good at diagnosing the masses. Yeah, if it turns out that viewing angle effects are really important, then you run into a bit of a problem, because we can have all of these different components of ejected masses, and they can be more or less pronounced depending on the system and how things go. So then you could end up kind of coming up with this very complicated architecture, the signal of which changes a lot depending on where you're looking at it from. But overall, we're a little bit lucky here relative to the supernova case, because all of our material is radioactive. So if we can get a good handle on what the radioactivity is and measure the energy being released through that, that should give us a fairly tight constraint on the mass. We don't have to do what we do in core collapse supernova and say, like, okay, but only a small fraction of it is nickel and the rest of it is just there. We can, if we're able to measure the luminosity, especially at late times when the transient is no longer photospheric and you're just kind of directly seeing the luminosity that's a result of radioactive heating, I think that would be really useful information.
From the online audience.
Oh, there's
details of the beta decay properties of our processed isotopes matter.
On kilonova timescales, we find that they're not so important. So beta decay is important for the kilonova because it's these energetic electrons from the beta decay that kind of heat up. They crash into the atoms in the surrounding medium. They heat it up, and that's where you get your thermal energy. You convert the kinetic energy of beta decays into this thermal energy that we measure as luminosity. So depending on the energies of the beta particles, they can be more or less efficient at heating the ejecta, and that can give you a small effect on your luminosity. But we're saved from having to think about that too much by the fact of timing. So, the kilonova radiation is important starting a few hours after merger, and and persisting days to weeks after merger. So on those timescales, all of the really unstable beta decaying elements with very short half-lives have already decayed away. And so you're left with things that mostly have half-lives on the order of the expansion time. And since you have this relationship that the Q of the beta decay varies inversely with timescale, you kind of have, just by the fact of when you're looking, you're dealing with more stable things that tend to have beta spectra that are one kind of, they're not energetic enough. Their energies are low enough that they pretty efficiently heat the ejecta, and then they don't vary that much from isotope to isotope.
When I think of the merger itself, I think of it as a kind of event where the outer crust first collides, then the inner crust, and then the core, or should I think of it all happening at once, and then you start the clock? Could some processes starting further than others?
Oh, which processes? Like, yeah.
Merger itself, would the outer portions be colliding first, and then some processes have a head start in terms of current?
Do you mean like some mass ejection processes or some? Yeah, I mean, well, so yeah, I mean, you're right. You're right that like the crust will collide, and then the inner material and the core. But I think that the different mass ejection mechanisms that we talk about are already kind of distinct in time. So you have this, or I mean, as distinct as something can be for a process that happens over hundreds of milliseconds, but you have kind of this tidal ejection, and that happens like in the immediate lead up to the merger. Then you have this crashing together, and my understanding of that is that's just kind of thought to release this material from the interface kind of in a single episode. And then the disk, you have outflows from the disk, but that's removed in time anyway from this initial mass ejection event. So yeah, to be honest, that's not something I have ever thought about before as far as is it going to matter that you are kind of colliding different parts of the neutron star in sequence. No, my sense is that you can think of any mass ejection that you get from that particular part of the merger just as kind of a single event that happens all at once. But I think it's a great question.
So of course the rate is very uncertain, like you said.
Yeah.
But one thing that caught my eye in your paper, that given the seemingly large amount of mass that was projected, if you look at the rate on the higher end of what the uncertainty allows, you actually might have the opposite problem, that you have overpowered our process.
Yeah.
So I'm curious, if there would be a potential explanation that would explain that.
Just how to avoid making too much gold.
No, I mean, what if our neutron star merger rates that we observe are really high
and they're all massive?
Yeah, and they don't look like what we see in galactic abundance.
That would be concerning.
That would be a nice problem.
Yeah. I mean, I guess we'll have to wait and see. It'll be, right. So I think part of the question is just, have we accurately inferred the parameters for this particular explosion? And then part of it is, is this typical of mergers, or is this going to be something that's on the bright end, and most of them will produce a lot less material, or will produce a lot more of the lighter R process. But yeah, I mean, if it turned out that we were lucky enough to observe a lot of these, and the abundance patterns we were inferring from them were not in line with the standard R process abundance pattern, that would be a conundrum.
One last question.
Yeah, what is the magnitude of the Doppler shift of the spectral lines?
Oh,
10%
there isn't. There is. So we can't like measure the. We don't know what the lines are, and so we can't measure the blue shift of any particular line. All we can do is get a handle from the level of line blending on what we think the velocities are. But yeah, we are not at the level of precision right now where we can have particular lines that we think are important and look for them in the spectra and then measure. No. No, I mean, so sorry, let me see if I can get back. Right, like if you look at if you look at the observed spectra, you can pick out by eye what you think are some features, but you don't know where those features what they correspond to in real life, or even if they correspond to 1 line or 10 lines, or what those transitions might be. And then, we're kind of estimating what we think the velocity is by looking at these synthetic spectra. But again, these, the features that we get from these synthetic spectra, one, are based on atomic structure models that we just don't have the capacity to calibrate to like the level of knowing that individual lines are correct. And then also, yeah, you still have line blending. And so kind of what we're assuming is that we statistically get the right number of strong lines in roughly the right places in wavelength space, and those are blending in a way that probably mimics the blending that happens in the real supernova.
Okay, let's thank Jennifer again.
Okay, thank you.